Ladies and gentlemen, welcome to this seminar on differential scanning calorimetry, or DSC as it is usually called. DSC is the most frequently used technique in thermal analysis. It is used to study the behavior of materials as a function of temperature or time. Melting points, crystallization behavior, and chemical reactions are just some of the many properties and processes that can be measured by DSC. In the course of this seminar, I would like to explain the basic principles of differential scanning calorimetry and introduce a high-performance DSC instrument. I also want to point out a number of important design features and explain their functionality. Finally, I will present several examples to illustrate different application possibilities of DSC. Differential scanning calorimetry measures the heat flow produced in a sample when it is heated, cooled, or held isothermally at constant temperature. A sample may undergo one or more phase changes during heating or cooling. A good example of a phase change is the melting of ice. The picture on the left is a winter view of Lake Seal in Switzerland. The surface of the lake often freezes over due to sub-zero temperatures. The water then exists in the solid phase as ice. In spring, when the temperature rises, the ice melts and changes from the solid to the liquid phase. The phase transition occurs as a result of energy exchange with the environment. The melting of ice to water can easily be measured by differential scanning calorimetry. The DSC measurement curve shows a peak whose area corresponds to the enthalpy involved in the process. The schematic DSC curve on the right of the slide shows typical thermal effects that occur when an amorphous plastic, such as polyethylene terephthalate, is heated. These include the glass transition, labeled 3, the peaks due to cold crystallization and melting, 4 and 5, and finally decomposition, 6. In a DSC experiment, the heat flow from the furnace to the sample is measured relative to the heat flow to a reference material. The sample and reference crucibles are identical, except that the reference crucible is usually empty. The schematic diagram in the upper part of the slide illustrates a heat flux DSC. In this particular design, the sample and reference crucibles are heated from below. The heat flow is indicated by the red dots in the diagram. The sample is placed in a crucible, or pan, which sits directly on top of the sensor. Both the sample and reference crucibles are surrounded by a heated chamber or furnace. The sensor is the heart of the DSC and detects the heat flow. The lower left corner of the slide shows an enlarged view of a Mettler Toledo sensor with its typical star-shaped arrangement of thermocouples. The star shape is formed by the many thermocouples incorporated in the sensor. The thermocouples guarantee that the heat flow is accurately measured. The measurement curve in the lower right corner of the slide shows a typical melting peak. The curve provides valuable information such as the enthalpy of melting, the melting point, and the specific heat capacity. This slide shows a schematic view of the furnace in a DSC-1 instrument. The heated parts are colored red, the cooled parts blue, and the DSC sensor green. The temperature sensor inside the silver furnace regulates the temperature via a heater, colored black, just below the silver furnace. A cooling option is often necessary to perform experiments below room temperature. Cooling is achieved by means of a flow of air around the furnace, or by using a cryostat or an intracooler. When an intracooler is used, a cooling flange is placed around the oven for direct and effective cooling. For cryostats, a cooling flange is provided that holds the cooling finger of the cryostat. Depending on the temperature range of the measurement, either one or both of the gas inlets illustrated in the diagram are used. The standard inlet is the purge gas inlet. If a cooling option is employed, the dry gas inlet is also used to prevent condensation from occurring inside the instrument. Samples can still be easily loaded into the furnace when the dry gas inlet is used. The sensors in the Mettler Toledo DSC1 are the most important components of the instrument. They determine the quality of the measurement. Two different sensors are available for the DSC1. The most frequently used is the full range or FRS5 sensor. The high sensitivity or HSS8 sensor is recommended for samples that produce only a very low signal intensity. The bottom part of the slide displays the results of tests that compare the sensitivity and resolution of both sensors. Better sensitivity means that it is possible to detect smaller thermal effects in the sample, or conversely, to use smaller sample amounts. The measurements were performed according to the so-called TAWN test guidelines, a universally recognized procedure used to test the performance of DSC instruments. In the lower left corner, the sensitivity is measured using the phase transition of a liquid crystal, 4,4-azoxyanisole. In the test, a 0.25 milligram sample of this substance was heated at the very low rate of 0.1 degrees per minute. The diagram shows that both sensors exhibit excellent sensitivity. The measurement curve of the HSS8 high sensitivity sensor demonstrates that it has a slightly better signal-to-noise ratio than the standard FRS5 sensor. The diagram in the lower right corner shows the TAWN resolution test for both sensors. Here, resolution means the ability to separate close-lying effects. In this case, the large melting peak at about 118 degrees was clearly separated from the small liquid crystal transition at about 135 degrees. The experiment was performed at a heating rate of 20 degrees per minute using 5 milligrams of sample. The results demonstrate that both sensors exhibit very good resolution. The measurement curves also show that the response of the FRS5 full-range sensor is faster than that of the HSS8 high-sensitivity sensor. Another important performance property in a DSC experiment is the baseline. The baseline should be free of artifacts or drift because effects like these could overlay or hide true sample effects. The diagram in the middle of the slide shows the very good baseline performance for both the DSC1 sensors. This confirms that the measurements display real sample effects and not artifacts. For quantitative heat flow measurements, the crucible containing the sample must have excellent thermal conductivity and be in optimum contact with the sensor. Thus, the geometry of the crucible and the material used are very important irrespective of the kind of sample that is measured. Mettler Toledo offers different types of crucibles to suit different sorts of samples. Some of the most commonly used crucibles are shown in the slide. Top left is the standard DSC crucible. These crucibles are light and sturdy and are easy to handle. They are made of pure aluminum to ensure good thermal conductivity. The crucibles can be hermetically sealed, left fully open, or covered by a pierced lid. The diameter of the hole in the lid determines the degree of gas exchange with the surroundings and can therefore influence evaporation or reaction processes. Depending on the sample and measurement requirements, other crucibles may also be needed. For example, gold crucibles are available for samples that react with aluminum. A common application is to measure a sample in a closed atmosphere and at a higher pressure than ambient. These measurements can be performed using the high-pressure crucible shown bottom left. The slide shows only a small selection of the crucibles currently available. In fact, there are more than 25 different types of crucible to match the requirements set by the sample and application. The DSC-1 instrument can be fitted with optional accessories for specific applications. The slide shows the different DSC modules offered by Mettler Toledo, from left to right: DSC microscopy, DSC photocalorimetry, high-pressure DSC, and DSC chemiluminescence. DSC microscopy is used to visually observe sample effects in the crucible and hence aid interpretation of the DSC curve. The visual information allows you to identify solid-solid transitions, to distinguish between overlapping processes such as melting and decomposition, to study the shrinkage behavior of fibers or films, or to identify the cause of an artifact in DSC curves. DSC photocalorimetry enables you to measure enthalpy changes in a material during and after exposure to light. You can investigate the effect of light on the behavior of light-sensitive materials. Typical applications include the study of light-activated curing processes, the effect of UV stabilizers, and the influence of light intensity on polymer stability. High-pressure DSC is used to study the influence of pressure on physical and chemical changes. Measurements at higher gas pressures offer advantages such as shorter analysis times because higher pressure accelerates reactions, for example, oxidation. The technique allows measurements to be performed under real process conditions. Overlapping effects can often be separated because evaporation is suppressed. Oxidation can be promoted or prevented by performing measurements under special atmospheres. Measurements involving toxic or combustible gases are also possible. DSC chemiluminescence allows you to detect the light emitted by a chemical reaction. For example, the chemiluminescence originating from oxidative degradation processes in polymers. This allows you to study the effect of stabilizers in polymers. In the food and pharmaceutical industries, chemiluminescence is used to obtain information about the stability of various products such as oils or fats. DSC measurements can be performed dynamically using a linear temperature ramp, isothermally, or with temperature modulation. Temperature scans are used to investigate temperature-dependent processes such as the glass transition, crystallization, melting, and curing reactions. Isothermal temperature experiments are mainly used to determine the oxidation-induction time of materials or to study chemical reactions. Temperature-modulated experiments enable you to separate reversing and non-reversing effects. For example, the glass transition from simultaneously occurring reactions or evaporation. Special atmospheres, such as pure oxygen or nitrogen, are often used in specific applications to accelerate or prevent the decomposition of samples. Most DSC measurements are performed dynamically using a linear temperature ramp. Here, the sample is heated or cooled at a constant rate, and the different states of the sample are measured as a function of temperature. The DSC curves in the slide show typical temperature scans of a sample of amorphous polyethylene terephthalate, or PET. The red curve shows the first heating run. It illustrates the typical effects observed on heating. The first event is the glass transition, which is seen as a step in the curve. This is followed by an exothermic cold crystallization peak and an endothermic melting peak. If the PET sample were heated to higher temperatures, it would start to decompose. The temperatures at which these effects take place are characteristic for each particular material. DSC curves can therefore be used as fingerprints in quality control. The first heating curve of the original sample also contains information about the processing history of the sample. In general, it is often very useful to measure the cooling curve of the sample and then record a second heating run. These additional measurements provide more information about the behavior of the material. The blue curve shows the second heating run. The glass transition is now no longer accompanied by the endothermic peak due to enthalpy relaxation. This effect is clearly visible in the first heating run and is related to physical aging of the material. Furthermore, there is no exothermic cold crystallization peak. This indicates that the cooling rate of the sample was low enough and that there was sufficient time for the material to crystallize. The crystallization peak can be seen in the cooling run shown black in the diagram. In contrast, the original sample was almost completely amorphous because the cooling process during manufacturing was too fast for crystallization to occur. The example shows that a great deal of information can be obtained from just one sample using a simple heating-cooling-heating cycle. In an isothermal experiment, changes in the sample are measured over a certain period of time, during which the temperature is kept constant. This measurement mode is used to obtain information about the time that elapses before an effect occurs, or about the duration of an effect. For example, in the determination of the oxidation induction time, the parameter of interest is the time that elapses before the sample starts to oxidize at a particular temperature. On the other hand, studies of chemical reactions allow information to be gained about the rate and duration of curing reactions. The example in the slide shows the curing reaction of a powder coating. Powder coatings are usually sprayed onto the substrate and then cured either thermally at about 180 degrees Celsius or by means of a UV light at lower temperatures. Curing with UV light has the advantage that temperature-sensitive substrates can be used and that hardly any volatile organic compounds are released. In practice, the main question is how long the material needs to be exposed to UV light in order to achieve an adequate degree of cure or cross-linking. This is illustrated in the slide, which shows several experiments that were performed to measure the degree of cure after exposure to light for different times at 110 degrees. The optimum exposure time can be determined by observing when the exothermic reaction peak is complete. In practice, incomplete curing as a result of vitrification is one of the most frequent causes of failure in composite materials. If an incompletely cured material is heated in a DSC, a so-called post-curing peak is observed immediately after the glass transition. The glass transition, post-curing enthalpy, and the original degree of cure can be determined by performing a temperature-modulated DSC experiment. In the example shown, the purpose of the analysis was to assess the quality of cure of a carbon fiber epoxy composite. This is usually done by measuring the glass transition temperature. In this case, however, the post-curing reaction and glass transition overlap. The green conventional DSC curve shows only a single exothermic peak. The experiment was therefore repeated using TOPM, a DSC temperature modulation technique. The glass transition is now clearly visible at about 210 degrees Celsius in the red reversing heat flow curve. The small peak in the blue non-reversing heat flow curve is therefore due to the post-curing reaction. The glass transition temperature and the reaction peak can be used for quality control. Temperature, gas exchange, and the type of atmosphere are parameters that influence sample behavior. Oxidation is a topic of considerable interest, especially in the field of plastics and oils. Oxidation behavior and stability can be studied by heating a sample rapidly to a predefined temperature in an inert atmosphere, usually nitrogen, and then switching over to a reactive oxygen atmosphere. The time that elapses before the sample starts to oxidize is known as the oxidation induction time, or OIT for short. The OIT is directly related to the relative stability of a material at a particular temperature. The example shown in the slide shows the OIT curves of 3 polyethylene samples that had been stabilized to different extents. The samples were measured at 210 degrees Celsius in open crucibles. As you can see, the difference in oxidation stability of the 3 samples is quite considerable. I mentioned earlier in the seminar that DSC has a very wide application range and that the method can provide a great deal of information. This next slide summarizes the main areas of application. One of the most important applications is the characterization of samples according to their material-specific properties, such as melting, crystallization, and change in enthalpy on heating. The glass transition temperature can also be used to characterize materials, but this transition is an important physical property in its own right. Thermal stability, as defined by the oxidation induction time or the decomposition temperature, is an important quality control parameter. Other types of chemical reactions and their kinetics are also important, for example for studying the properties of adhesives and thermosets. In the pharmaceutical industry, the main applications concern the detection and study of polymorphic forms and the analysis of impurities in active ingredients. DSC has many potential applications and is used in a wide range of industries. This slide presents an overview of the different industries and applications. The table shows that DSC is widely used to determine the glass transition and investigate chemical reactions, melting, and crystallization. Other DSC applications deal with the influence of additives, fillers, or the processing of materials. The characteristic shape of the individual DSC curves is used for quality control. I would now like to present several different application examples that demonstrate the analytical power and versatility of the DSC technique. The slide shows an example of polymer fingerprinting and identification. The different plastics shown in the diagram can be identified by measuring the temperatures at which they melt. The melting peaks of the polymers clearly differ in their size and position on the temperature axis. The melting peaks of polypropylene, PP, and polyoxymethylene, POM, show that identification depends both on the melting temperature and on the enthalpy of fusion, which is the hatched area under the peaks. If the type of polymer is known, the degree of crystallinity can be determined by integrating the area. This is shown for polypropylene as the blue hatched area in the diagram. Glass transition temperatures can also be used to identify and characterize polymers. The glass transition is observed when an amorphous material is heated and changes from the rigid glassy state to a soft rubbery state, or vice versa on cooling. There is no uptake or release of latent heat, only a change in the specific heat capacity. Parallel to the previous example, the slide displays the glass transitions of several thermoplastic polymers. The thermal and oxidative stability of materials is a very important quality characteristic because many materials decompose at higher temperatures and become unusable. Stabilizers are often added to the product to counteract this effect. The thermal stability of a substance can be measured by using a purge gas that reacts with the sample. In most cases, this is oxygen. This slide shows an example of the determination of the oxidation onset temperature, OOT, of different edible oils. In an OOT experiment, the sample is placed in an open crucible with unrestricted access for oxygen gas. The temperature is then ramped at a constant rate until exothermal decomposition of the sample begins. The oxidation onset temperature is evaluated as the onset in the measurement curve as shown in the diagram. The slide shows that the various edible oils have different thermal stabilities. Another important application of differential scanning calorimetry is to measure the curing reaction and glass transition temperature in epoxy resin systems. The diagram displays the DSC curves of several samples that had been cured to different extents. The results show that with increasing degree of cure, the glass transition shifts to higher temperatures and the enthalpy of the post-curing reaction decreases. In the diagram, the degree of cure increases from top to bottom, starting with the red curve of the uncured sample to the green curve of the fully cured sample. If the reaction enthalpy of the uncured material is known, the degree of conversion before the measurement can be calculated from the enthalpy of the post-curing reaction. The conversion is directly related to the degree of cure, which is shown on the right-hand side of the diagram. The upper inserted diagram shows the relationship between glass transition temperature, Tg, and the reaction conversion or degree of cure, alpha, determined from the DSC measurements. Kinetic analysis is used to study the rate at which a reaction proceeds. The slide summarizes the steps involved in kinetics analysis using the so-called model-free kinetics, or MFK procedure. The method is based on the measurement of several dynamic DSC measurements. In step 1, the exothermic reaction is measured by DSC at 3 or more different heating rates. The reaction enthalpies are then determined by drawing suitable baselines and integrating the areas under the peaks. In step 2, the data obtained in step 1 is used to calculate conversion curves that show the extent of reaction or conversion as a function of temperature for the 3 heating rates. In step 3, the model-free kinetics program calculates the conversion-dependent activation energy from the conversion curves. The diagram shows that, in this example, the activation energy changes during the course of the reaction. This indicates that more than one mechanism is involved in the reaction. The activation energy calculated is therefore referred to as the apparent activation energy. Finally, in step 4, the results from the preceding steps are used to make predictions about reactions. For example, to predict the conversion curve as a function of time at an isothermal temperature of 170 degrees. We can then, for example, read off how long it takes to reach 90% conversion. According to the curve and table, the time required is approximately 30 minutes. This prediction was checked by performing an isothermal measurement at 170 degrees and overlaying the measured and predicted curves. Clearly, the two curves match very closely. To safely process and store chemicals, it is important to know the temperature at which they start to react, the reaction rate, and the energy released in the reaction. The safety measures that have to be taken when processing or storing a particular substance can then be assessed. Chemical substances that contain one or more nitro groups are well known for their explosive potential. Some of these products, for example picric acid, trinitrophenol, are starting materials for chemical syntheses or are used for analytical purposes. Others find use as propellants or explosives, for example nitrocellulose or ammonium nitrate. The latter as fertilizer has already been the cause of several very serious explosions. The slide shows DSC measurements of 3 of these thermally hazardous substances. The results provide information about the starting temperature of the reaction, the reaction rate, and the energy released when such substances with very large exothermic reaction energies decompose. For example, the enthalpy of reaction of 3,450 joules per gram for picric acid under adiabatic conditions would cause a temperature increase of more than 1,000 degrees. Analysis of the melting behavior of a substance is an important method used for the quality control of pharmaceutical products. The melting curve yields information about polymorphism and allows the degree of purity to be determined. For example, the red curve in the slide shows that the metastable modification of the substance melts at a lower temperature than the stable modification. The melt then crystallizes to the stable modification and afterwards melts at a higher temperature. Knowledge of the particular crystalline form present is very important for assessing the physical stability and bioavailability of active pharmaceutical ingredients. The percentage purity of a substance can be determined by evaluating the melting curve using a method based on the Van 't Hoff equation. In this example, this is shown by the blue curve for the stable form of phenobarbital. Differential scanning calorimetry is an excellent technique for characterizing the thermal properties of materials such as thermoplastics, thermosets, elastomers, adhesives, chemicals, paints and lacquers, foodstuffs, pharmaceuticals, fats and oils, metals and ceramics. This slide summarizes the features and benefits of the DSC-1. The Mettler Toledo DSC-1 instrument measures heat flow very reliably with optimum resolution and sensitivity, so that even the weakest effects can be measured. For high-throughput applications, a sample robot allows easy automation of entire sample series, and even different types of crucibles can be measured with individual temperature programs. Because of its modular concept, options such as sample changers or cooling devices can be added later on if the need arises. Flexible calibration procedures allow the instrument to be calibrated and adjusted over the entire temperature range from -150 to +700 degrees Celsius. Finally, I would like to draw your attention to further information about differential scanning calorimetry that you can download from the Internet. Mettler Toledo publishes articles on thermal analysis and applications from different fields twice a year in UserCom, the well-known Mettler Toledo biannual technical customer magazine. Back issues can be downloaded as PDF files from the Internet as shown at the bottom of the slide. Individual applications can also be searched for on the Mettler Toledo homepage. In addition, you can download information about application handbooks, webinars, or of a more general nature from the internet addresses given on this slide. This concludes my presentation on differential scanning calorimetry. Thank you for your interest and attention.